Abrasive wear, in simple terms, involves hard particles rubbing against a softer surface, causing material to be removed. This wear can be further categorized into two-body wear, where one surface is harder than the other and removes material from the softer surface, and three-body wear, where the particle is harder than the surfaces it's trapped between. This wear is a common occurrence in various industries and plays a significant role in the maintenance and repair expenses of equipment. Envision hard particles grinding their way across a softer surface. They move, they gouge out material, leaving behind a trail of destruction. This isn't just an issue of aesthetics. As the abrasive wear persists, it can bring about serious structural problems, jeopardizing the integrity of the affected surface. Over time, this compromises the performance of machinery, necessitating expensive repairs or even premature replacements. If not monitored and controlled, abrasive wear can drastically inflate operational costs and reduce the lifespan of machinery. Thus, grasping this destructive process serves as the initial step towards effective mitigation and prevention. There are two principal kinds of abrasive wear which cause a large percentage of all lubricated machine failures worldwide. For instance, 80% of all hydraulic failures are caused by two-body and three-body abrasive wear, also known as cutting wear. Plunging right into the first category, two-body abrasive wear, this happens when one surface is harder than the other. A great example is in cutting tools which use metalworking oils to cut or shape a material. This is often part of a machine designed for this to occur and can actually be useful, but the lubricant choice helps control the process. You can picture it as two dance partners moving across the dance floor, but instead of a smooth waltz, it's more of a sandpaper tango, the cutting oil acting as a chaperone to prevent things going too far. Factors that influence this type of wear include the hardness, size, roughness, and shape of the contacting surfaces. Now, let's step into the realm of three-body abrasive wear, which is usually what most people are concerned about in terms of a fault mechanism. In this situation, there's an additional player: particles suspended in the fluid. These particles, like uninvited attendees at a party, interact with a surface to create indentations and remove material by gouging it out. The particles of most concern are ones about the same size as the fluid film thickness. Why do you think that might be? Well, smaller particles pass straight through, whilst larger ones are too big to get trapped in between the surfaces. Hence, there is a Goldilocks zone of particle size to cause maximum abrasive wear damage at similar to the film thickness of the oil. This wear is common in settings where airborne or fluid-borne particulates are highly probable. We've covered a brief overview of the two primary types of abrasive wear, the culprit behind 80% of all hydraulic failures, namely three-body abrasive wear. However, with the right understanding and strategies, we can control them, reducing maintenance expenses and extending our machinery's lifespan. Knowing the types of abrasive wear is essential in formulating effective preventative and mitigation strategies. Detecting abrasive wear involves a combination of visual inspection of individual component surfaces to see the damage caused directly, or by advanced microscopy techniques to see the particles created as a result of the damage. Let's delve a bit deeper into these methodologies. Visual inspection is usually quite a late step to spot abrasive wear, as that means the damage is no longer microscopic. However, it is still a useful tool in locating damage occurring. Imagine running your hand along a wooden table and feeling a splinter. This is a simple form of visual, or in this case tactile inspection, where the evidence of wear, in this case the splinter, is readily apparent. In the context of machinery, we are looking for signs of scratches, indentations, or any other form of material removal. These visual cues can provide us with an immediate understanding of the wear's severity and its potential impact on the machine's performance. However, not all wear is easily visible to the naked eye, and indeed visually inspections of small or hard-to-access components is often not practical. This is where microscopy of oil samples comes into play. By utilizing microscopy, we can delve deeper into the surface, observing the finer details that are not observable by a simple visual inspection. It's akin to using a magnifying glass to see the tiny wood grains that make up our hypothetical table. Microscopy allows us to identify the subtler signs of wear and tear, giving us a much more comprehensive view of what's happening in the system and much earlier. Elemental analysis of wear metals, including lube wear acid digestion, allow identification of the metal types and potentially component types wearing. However, you can build upon this. And here's where lube wear vision analysis takes the game to the next level. Lube wear vision analysis is a technique that integrates with the microscopy process to provide a precise identification of wear types. This gives specialist analytical ferrography analysis on a routine sample. It's like having a smart magnifying glass that not only lets you see the wood shaving but also tells you how those shavings formed. This combination of microscopy and lube wear vision analysis allows us to accurately identify and classify the wear, guiding us towards the most effective mitigation strategies. A key one of these wear types is cutting or abrasive wear. These can be spotted down the microscope as long and thin particles, usually curved and with a length to width of at least 10:1. Think of peeling an apple with a peeler. The long, thin, curly peel is what the abrasive particle is doing at the microscopic level to your components. The components themselves would show visible scratches, but the particles produced enter the oil and can be seen in the oil sample analysis. Early detection and thorough analysis of wear can significantly extend the operational life of machinery. By understanding the wear patterns and types, we can take proactive steps to prevent further damage, ensuring that our machines keep running smoothly and efficiently. So remember, a keen eye and the right tools are your best allies in the fight against abrasive wear. There are numerous techniques to counteract the impacts of abrasive wear. Let's dive into each of these to comprehend how they can safeguard your apparatus and equipment. This first bit might be more for machinery designers than end users, but is useful to understand when specifying machine requirements for your environment with an OEM. Kicking off with material selection, it's an essential initial step in countering abrasive wear by choosing materials high in wear resistance. This could entail opting for materials with high hardness, tenacity, or both. It's all about discerning the operational environment and selecting materials that can endure the task. The next strategy involves surface coatings or solid lubricants. Placing a protective layer like PTFE on machinery parts can dramatically decrease wear. These range from hard ceramics to soft polymers, each with their distinct advantages. They act as a shield between the abrasive particles and the surface, absorbing the force and preventing direct contact. Subsequently, design optimization, which reduces areas of abrasive contact through smart machinery design, plays a key role. This could mean streamlining shapes, minimizing exposed surfaces, or even reorganizing the entire system layout to create a design that lessens the chances of abrasive wear. Remember, prevention is better than cure. The final strategy is contamination control, and I have left this until last, as this is the most common cause of machinery damage with abrasive wear. Let me repeat that, as it's very important. Contamination control is crucial to reduce abrasive wear, and is the single biggest thing you can impact to help component life. It's vital to implement methods to lessen particulate infiltration in systems, either through high-quality seals, effective filtration systems, breathers, or maintaining a clean operational environment. These are steps you don't do once and then forget about. They are lifelong steps you perform as part of regular maintenance to keep your equipment clean and healthy. Every step counts, and you're better adopting practices you can maintain rather than doing the deluxe option once and forgetting about maintenance after that. To summarize, mitigation strategies for abrasive wear comprise material selection, surface coatings like PTFE, design optimization, regular maintenance, and contamination control. Each contributes to a holistic approach that directly addresses wear and works in advance to prevent it. Implementing these strategies can substantially decrease wear and lengthen machinery's lifespan. But it's crucial to note, the most effective approach is a balanced one, considering all the operational environment's aspects. Preventing abrasive wear holds equal, if not greater importance, than curbing its effects. Let's delve into the efficacious preventative measures one can implement. Primarily, contamination control is the answer. This can be accomplished by employing air filters, seals, breathers, and the like. Such design changes are typically made by original equipment manufacturers, OEMs, rather than end users, but maintaining them is important, and indeed considering additional offline filtration may also complement the cleanliness strategy. Furthermore, regular cleaning of both the machine and its immediate environment is imperative to reduce particle buildup and consequently decrease the risk of abrasive wear. Finally, proactive replacements should not be overlooked. By promptly replacing components that exhibit initial signs of wear, we can nip the potential issues in the bud and avert greater damage in the future. Remember, these preventative strategies are not solely to extend the lifespan of your machinery, but also to curtail costs. By lowering the risk of abrasive wear, we can significantly diminish maintenance and repair costs. Thus, preventative measures can significantly decrease the risk and accompanying costs of abrasive wear. Oil analysis plays a critical role in detecting early signs of abrasive wear. It's like a detective, hunting out the clues that point to potential problems within our lubricated systems. By examining the particles suspended in the oil, particle count monitoring, and wear metal analysis, we can identify the type, severity, and source of wear, allowing us to take action before substantial damage occurs. This is where predictive or condition-based maintenance comes into play. You can check our other videos on these topics to get more detail on what predictive, proactive, and condition-based maintenance mean. By analyzing oil samples on a regular basis, we can anticipate issues and address them proactively, preventing costly breakdowns and extending equipment life. Now let's talk about lube wear. Their advanced techniques take oil analysis to the next level. By integrating visual and microscopic evaluation, lube wear can precisely identify the level of abnormal wear present and confirm it with the wear types by lube wear vision to predict the wear progression. This enhanced accuracy leads to more effective maintenance strategies. So remember, oil isn't just a lubricant, it's a valuable source of information. Effective use of oil analysis can lead to significant cost savings through predictive maintenance. Understanding and combating abrasive wear is crucial in maintaining the operational efficiency of machinery. As we've seen, abrasive wear is caused by hard particles rubbing against a softer surface, and it's a significant factor in equipment maintenance and repair costs across various industries. We've explored the two main types of abrasive wear, namely two-body and three-body, and how they occur in different settings. We've also delved into the techniques for detecting wear, from visual inspections and microscopy to advanced oil analysis methods. Moreover, we've discussed strategies to mitigate wear, including the selection of wear-resistant materials, application of surface coatings, design optimization, regular maintenance, and contamination control. Looking ahead, advancements in material science and predictive maintenance technologies are set to play a pivotal role in managing abrasive wear more effectively. Lubricant analysis is a lifelong guide to help you manage and make informed decisions about your machinery condition. Identify contaminants proactively before they cause wear. With the right knowledge and tools, abrasive wear can be effectively managed, leading to significant cost savings and extended machinery lifespan.